HellermannTyton's Technical Director. I'm going to spend the next 30, 40, hopefully more than 5 minutes anyway, telling a couple of stories around the thing that we're all here to hear about, hopefully learn something about this afternoon. I've been coming here, not standing in front of you people for quite a while, and over that period of time, I think definitely the content of these presentations, the main emphasis of these presentations has clearly shifted from something that originated in the data center, originated in the enterprise, to something clearly based on what you've heard about this afternoon already, something that's much more outside plant and maybe triggered by the massive explosion that we're seeing in the fibre to the home space at the moment. People much more interested in blowing, floating fibres in ducts, getting fibre to the home, getting people connected to the internet, facilitating remote working. But of course, the latter can't help without the former, and the former wouldn't be seeing some of the explosion it's seeing without the latter. And what I wanted to try and do with this presentation was just pick a few aspects of this industry, the technologies that are underlying it, underpinning it, but actually how they really are all complementing each other. We wouldn't be able to enjoy Netflix, of course, assuming that we do, without the data centers that serve that content. At the same time, we would struggle to work from home again, as some of the stories today would definitely allude to, without that fibre to the home infrastructure. And so bringing those things together, putting some stuff at the front end, putting some stuff at the back end, really being able to drive that content and how it comes to be, again, is really what I'm hoping the next 30 or 40 minutes or so will get across. But actually, as HellermannTyton, we're not providing any of those smart bits at either end, with the bits with the flashing lights, the bits with the silicon in. Our product portfolio, and this is the last I'll mention of it, is just the physical layer. But of course, without that physical layer, those flashing lights don't really have anywhere to go. And the presentation, though, is really about the stuff that's going on at either end whilst utilising that physical layer. And it does a jump between fibre to the home, data centers, micro points of presence, wavelength division, multiplexing, just a bunch of different technologies that some are being used today, maybe being used in different sectors of the industry, some that may well not quite have reached their full potential or their full maturity. I'm not going to read through the words on the slide, please do, should you be so inclined. I'm just going to pick out a few points, again, tell some stories, and hopefully just provide some things to think about, some directions that certainly from my vantage point I see the industry moving in. We are seeing, I beg your pardon, a lot of building, overbuilding in many places, which again has got some interesting implications and ramifications to our urban spaces. But we're seeing more and more of those operators based on sort of government guidelines, government insistence, having to work in ever more rural spaces, and there are people in the room that are definitely part of deploying fibre to the home in the extremes of rural spaces. But from a physical layer perspective, and again, I'm not really even talking about a civils perspective, and that's definitely not my sweet spot, but from a physical layer perspective, there are things that are being done differently, can be done differently, based on nothing more than population density. We see in a more urban setting, optical split ratios, the ability to take the signal on the fibre and split it in half and serve 2 customers, and take that and split it in half and serve 4 or 8, 16, 32, 64, even 128 subscribers from a single fibre, which is great if you've got a very dense environment where you can reach those 128 subscribers fairly effortlessly. But that's not always the case in a rural or extremely rural environment, where the investment, the cost of switching that laser on and having it deliver to 128 subscribers could be spread over countless, almost, square kilometres. We're starting to see some operators that we're dealing with on a very regular basis change up the way that they are splitting those fibres, the ratios of splitting that they're deploying, whether it's in underground joints, whether it's in telegraph pole top boxes, wherever those connections are made, instead of deploying high split ratios in a centralised location, they're distributing those along through a wider area to consolidate some of that OPEX, because the flashing lights, the OLTs, the transceivers that are being used, whilst they have a CapEx associated with them, they also don't run forever, they don't burn forever. Eventually they wear out, eventually they need to be replaced. That has a cost associated with them. And we're seeing those split ratios perhaps firstly be reduced. 128 maybe in a rural space is difficult to achieve. 64 maybe even difficult to achieve. 32 split ratios maybe make more sense, although with different technologies we can switch that up. We see some circumstances where 1x16s may be cascaded with some 1x4 way splitting, where that might work in some scenarios, but we're definitely seeing trends towards reducing that split ratio closest to the subscriber to really optimize the investment associated with the active electronics. So that cost to deploy, that cost per home, and again, I'm not going to get into a debate over homes passed or homes connected. We really don't have enough time for that this afternoon. But to provide those fibre connections, most importantly, to as this separate number of subscribers as possible, is definitely made more efficient, both commercially and from an implementation perspective, by switching up some of those split ratios closest to the subscribers, which again is very different to certainly the current OpenReach model, for example, where they deploy single 1x32 way splitters throughout the majority of their network. What we're also seeing in that rural space, and we're going to take some of this and drop it into other parts of the presentation, is deploying small, maybe even village-based micro points of presence. In fact, the village here, I'm fairly sure, was fibred by the service provider GigaClear. And I can say that just based on which side of the cabinet the doors are hinged as I drove in. And obviously they are a rural, substantially underground, but certainly a rural service provider. They provide a point-to-point connection, so they've literally got active switches inside a micro point of presence. There is an active street cabinet somewhere in the village. I didn't see it as I drove past, but serving the passive point-to-point cabinets in the village. And they may not, I'm not sufficiently familiar with their network, utilise some of the things that I'm going to talk to you about in a moment with regards to wavelength division multiplexing to optimise dark fibre usage throughout those micro pops. But the fact that they have them, the fact that they can build this very disaggregated network and potentially route a large number of fibres between those nodes, and again the first presentation this afternoon was talking about redundancy and resiliency and building rings and having multiple points of interconnection between the different stations, again to ensure resiliency within the network is all part of what we're seeing happening, certainly with regards to that very rural space, to ensure permanent, trouble-free, error-free connections. We're also, which is an extension of that sort of rural discussion where split ratios are being changed, in some instances fully reversed. This is something that truthfully I haven't seen in the UK yet. It is something, an approach that we see taken in the US. Am I battery flat?
Maybe.
Sounds like it. How's that? Something's working. Is that better?
Yes.
Yeah. Beg your pardon. So in this scenario, instead of dropping a number of customers at every single node, actually we're just dropping a single fibre to a single customer, where we have an amount of distance between adjacent residences, large farms, for example, in a very rural network. You can serve those, in this particular illustration, a dozen properties, not using a dozen fibres, but actually just using a single fibre, which it might be an interesting thing for you to hear somebody that sells fibre optic infrastructure for a living. Actually, you don't need to blow a 12 fibre cable, potentially blow down a duct and have each one of those fibres serve a separate customer. In this scenario, I'm actually serving all of these customers, maybe separated by 5 kilometres between adjacent properties, using a single fibre and still providing that fibre to the home experience, still able to support 1 gig, truthfully still able to support 10 gig using technologies like XGS-PON, but not requiring such a high density of fibre. And again, in a reasonable number of circumstances and installation environments, fairly easy to get that amount of glass into that space. But if you are covering a very, very long distance, the cost of that fibre may well be unacceptable, whereas in this alternative scenario, and it's not suitable for every installation case, I can reduce the amount of fibre needed to serve all of those customers. More typically, you would have a centralised node that would serve 4 customers, and then further down another centralised node. But this is just something that we're starting to see as interesting in MDU spaces as it is in actual full sort of outside plant style installations. For those of you that are truly familiar with more conventional splitters and split ratios. This insertion loss actually is artificially high based on this technique compared to a normal split ratio, but where it saves, of course, is the cost of the actual fibre deployment. Something that we don't see a great deal of, especially when you're talking to homeowners that have had workmen at the end of their road for days, weeks, and in some instances months on end, deploying a fibre to the home only for them to be replaced by a second set of contractors that are going to do the same in the same place. This whole notion of overbuilding because our ability to unbundle the network has not been truly considered. There are some service providers that will share some of that infrastructure, but we see in other parts of the world actually the network is truly unbundled. There is only a single fibre to each of our homes. We're not in a scenario where our home's got a BT box and a Virgin box and a City Fibre box and somebody else's box, and depending on who it is that we have signed up with at the moment, the front of our homes are getting busier and busier, especially when we've got our EV charger unit out the front there as well, and whatever else it is. We have and are starting to see some unbundling, some fibre unbundling, certainly from a rural perspective, and it's difficult to get, expensive to get certainly from a civils perspective, large amounts of fibre into those very remote locations. We're starting to work with customers where they're actually now unbundling some of that fibre, literally taking it out of, in this particular instance, a rollable ribbon-based cable deployment, a high-density blowable cable design, and offering some of those fibres as part of their network to, in essence, some of their competitors, some of their partners, and really being able to unbundle the fibre. But we've also got technologies like wavelength division multiplexing, where we're not truly unbundling the fibre, but we are starting to passively unbundle some of the wavelengths that are available, so we can separate our customers, separate those suppliers from a wavelength perspective to really optimize the utilization of the glass that is in the ground. And wavelength division multiplexing, and certainly dense wave division multiplexing, is absolutely not something that's new, and it isn't something that certainly isn't new in that telecom space, in that long haul space, in that dark fibre space. Dark fibre is an expensive commodity to rent. Of course, generally speaking, it's much more expensive to put your own in, again, of course, depending on the length that you're travelling. But having the ability to share that resource, to unbundle at the wavelength level, really starts to open up what that fibre can do. Again, depending on the distances that you need to travel, the services that, as a service provider, you might or might not be interested in delivering. Fairly trivial today to support 32 channels or 48 channels at 100 gigahertz spacing. So the amount of bandwidth that's available per channel is still massive. There are other spacing grids available. This kind of depicts a coarse wavelength division multiplexing type grid spacing, and we're seeing fibre to the home cabinets, fibre to the home deployments combine both FTTH technology for residential customers or maybe some SMEs with wavelength division multiplexing, so that instead of the actual packets sharing the same wavelengths, to try and address some of the contention ratios, some of the broadcast issues, some of the upstream time domain issues associated with PON technology. We can utilise the same fibres, the same fibre bundles, and serve a multitude of different customers with different technologies. And we are starting to see from a connection from that micro POP or that active street cabinet out to specific customers, the cabinets having the ability to support GPON or XGS-PON from an FTTH perspective, but also the ability to incorporate wavelength division multiplexing technology for those SMEs that really don't like the thought of sharing their fibre with their nearest neighbours. And whilst, of course, WDM is still sharing the true fibre, you're absolutely separated by wavelength. And tools such as Wireshark and those other IP type physical layer sniffing tools are substantially less likely to prove what's going on, what traffic is being sent to and received from your neighbours if you've isolated in wavelength. And that's very different to the much more broadcast type technology of passive optical networks, where I suspect this isn't particularly new to any of you, but if you are connected to a fibre to the home network and you're connected to a splitter and the split ratio is 1:64, you and 63 of your nearest neighbours are sharing a substantial part of that fibre and a substantial part of it back to the data centre and the internet. And that single fibre is sharing all of that traffic. Everything that you're downloading and they're downloading is sharing that fibre, except until it gets into the ONU, where then the headers of the packet strip it out, and you are only getting what you're asking for, but you can kind of, with again tools like Wireshark, there are definitely ways around some of those things, whereas with the WDM technology, both coarse and dense, you can start to put some physical barriers up. And some SMEs really appreciate that differentiation. And I just wanted to show you what it looks like. Not everybody necessarily can sort of visualize, but this is a DWDM waveform, an optical spectrum analysis centered around the 1550 nanometers, so again, one of the core wavelengths that we test to. And this is showing the windows, the grid spacing of 32 channels of DWDM. And each one of those could represent a separate customer. But you can see that they're isolated from each other because of the way that the WDM operates. But in that scenario, we can support 32 separate customers over a single fibre, all transmitting and receiving using their own wavelengths, fully isolated from each other. And we can use some of that technology to, again, fundamentally minimize the amount of glass that we're putting under the ground in cases where we're perhaps using somebody else's, or there possibly just isn't enough room under the pavement or under the road. We're not the first people there. There are already countless other services that have dug that space up. There's no more room in Openreach's PIA network. How do we optimize what we want to deploy? And we're seeing customers, again, with their active points of presence, their sort of micro data centers, using this technology to drop off a couple of channels, add a couple of channels at multiple locations. And you can imagine if we start at data center 1, ultimately we want to get to data center 2, but in between those locations, we've got, other small villages, other areas that need that connection. And we can provide resiliency actually in both directions, start to introduce multiple points of failure, start to truly support dynamic routing protocols, and all of those layer 2, layer 3 and above technologies that are the backbone of providing us with our internet connectivity or our data center interconnect, again, depending on the technologies that we are most interested in deploying. And everything that's come before this slide, again, is really been about outside plant, connecting SMEs, connecting customers, fibre to the home, wavelength division, multiplexing. But I kind of wanted to bring everything back, at least I think for a slide, possibly 2, I'm sorry I don't recall, but bring everything back to how do all of those things that we just talked about get the ones and zeros that they're ultimately sending to their customers? Where does that data come from? Our demands for it are constantly evolving, and the technology that underpins that data center space, of course, is having to grow in line with our demand for more and more bandwidth, our need to have the data centers where we want them, our reluctance to wait for stuff to download, their absolute necessity to ensure that the data is backed up wherever it needs to be, can be delivered efficiently. The whole data center interconnect piece is a massive, massive industry. But the speed of that data provision is not standing still. Most of the people in the room, I expect, certainly I can recall first 10 gig transceivers, then 100 gig transceivers using 20 lanes, 25 gig transceivers, again, benefiting from a 25 gigabit baud rate, really then enabled us to support 100G base SR4, where I've got 4 lanes of transmit and 4 lanes of receive. We went to 100, we went 200, 400 gigabits per second. And I just wanted to show you how even 400 gigs not the end of the road. He mentions there 800 gig. But these technologies are they're all being developed by manufacturers, the likes of the IEEE, Cisco's and Broadcom. They're massive, massive contributors to this space. But without taking a great deal more of your time, both of these 2 configurations support 400 gigabits per second. The bottom one actually is the one that I'm going to start with. 400 gigabits per second, utilizing 50 gigabaud technology, and we've got 50, 100, 150, 200, 250, 300, 350, 400 gigabits per second. But I need a 16-way connector. I need a 16-way MPO, or MTP. Now, thankfully, there are at least 2 people in the room that have the capability to inspect these products, because I need 16 lasers working all at the same time. I need to know they're clean, I need to know they're not contaminated. 16 fibers to a line is a massive, massive number, but it's also, at the moment at least, fairly uncommon in any of our data centers because of just how new it is. But it is a great way of supporting 400 gig over multi-mode fiber. The connector above it is a standard 12-way MTP, and for those of us that have got data centers, work in data centers, or play with MTPs and MPOs, that's much more familiar, much more common to us. It's utilized with 100 gig today, 25 gig on the first 4, 25 gig on the last 4. But we've got 4 designated to transmit, 4 designated to receive. In this particular configuration, which is this 400G base SR 4.2, each fibre is, ignore the 4 in the middle, each of the used fibres are both transmitting and receiving at the same time. So we're using, again, we talked about wavelength division multiplexing, different wavelengths, different colours of light. In this instance, this single fibre is both a receive and a transmit. And we're having to combine parallel optics, 25 and 50 gigabaud lasers, wavelength division multiplexing in order to deliver 400 gig per second over multi-mode fibre. Now, that's an incredible feat of physics, engineering. It's also great because you're fairly able to utilise legacy infrastructure, and that's got to be part of the equation because the cost to replace that infrastructure is not always particularly palatable, not always efficient, not necessarily something that you can grow organically. But of course, multi-mode fibre is not the only fibre on the block. To this point, I've only been talking about single mode fibre. And there are other ways of achieving 400 gig and 800 gig with single mode fibres, but actually they're also using wavelength division multiplexing, and in some instances also parallel fibres. There are, really, I guess the take home is there's always more than one way of delivering and achieving the same. There's definitely, minimum 2 flavours of 400 gig over multi-mode fibre. There are others based on single mode fibre. And in actual fact, this is from the Ethernet Alliance. This isn't mine, I've borrowed it, stolen it if you will. But you can see here, multi-mode fibre, there are at least 4 different versions of 400G base SR short reach multi-mode. I've got a similar number when we start to get to single mode, and again, depending on how far I want that to push, there's lots of different flavors, and making sure that they're compatible in our data center spaces is by far and away one of the most challenging aspects of achieving that 100, 200, 400 gig. And the 2 images on the left-hand side start to break down the different ways that that's deliverable. So in this particular instance, 4 lanes of 100 gig, 8 lanes of 50 gig, or 16 lanes of 25 gig, but the sums are always the same. They always bring us back to 400 gigabits per second. There are ways of achieving higher data rates using multiple fibers, using multiple bandwidths, using multiple directions. In all of that technology, we're also starting to see the number of levels that are being transmitted along those fibers. By that I mean, this particular diagram is showing us 2 states of light, if you will, and those 2 states are hopefully obvious. The light's either on or it's off. It's sending a 1 or a 0. And that's kind of what we're trying to represent here. 1 is at the top, 0 is at the bottom, and I can send my 1s and 0s, my binary data, by either switching the laser on or switching it off, switching it on, switching it off. I can send my data. But that has a limitation in just how many bits per board, how much data I can actually send down my fibre. And then somebody did that. Wasn't happy with on and off. They went, aha, can we have it off on a little bit more, and then all the way on. And again, it seems like an obvious thing, but really the bit that limits this is how clear is this gap? How sure am I that I'm at the level that I'm supposed to be at? Because if I'm not sure, I'm going to transmit an error, and if I transmit an error, I've got to tell it that it sent me an error, and then I've got to ask it to send it again. Actually, everything's just going to slow down. This PAM4 encoding, instead of me sending 1 bit per board, 1 bit per cycle, I can now send 2 bits per cycle. I can double my data rate by using a much more sophisticated encoding scheme. And even this isn't the end of the story. People are talking about PAM8. Not quite sure what that would look like. Might need a bigger screen. And also talking about, you may have heard that some of the phrases, coherent optics. We're not just sending, we're not just turning stuff on or off. We're adjusting the phase of that light and actually the way that we send it down those fibers. And we're able to, again, encode much more information down our fibers, between our transceivers, as we start to increase and improve, make more sophisticated our encoding schemes. So there are a lot of things ultimately driving how we increase the number of ones and zeros that we're getting down our fibers, number of lanes, number of wavelengths, encoding schemes. They're all part of that. How can we make this stuff quicker? How can we get more ones and zeros to us? And really just, I guess, to bring it full circle, it's all about delivering ones and zeros to our homes, to our mobile phones, to those micro cells, those macro cells, those 4G base stations, those 5G base stations, public transport systems, underground systems, overground systems, and serving us in our ever increasing demand for data, and truly then bringing a lot of fibre into that MNO space. Of course, they're used to dealing with fibres, but they're used to dealing with it, in 2G cells, 3G cells, 4G cells. As we start to go 5G, as we start to go micro cells and macro cells, the amount of fibre being deployed, the amount of dark fibre, the opportunities for wavelength division, multiplexing, the opportunities to bring all of those technologies together makes for the industry, a bit of a cliche, it's a really interesting time to be part of what's going on. We've seen a massive boom very recently with fibre to the home, and we are starting to now see a good deal of that infrastructure being leveraged, not just by the service providers to deliver an FTTH solution, but to start to blur the lines between fixed and wireless infrastructure. There's a lot of fibre in the ground. There's probably not enough fibre in the ground, but you would expect me to say that. But I think there's still a phenomenal amount more that the industry will get it to do over the next 3, 5, 10, who knows. Certainly long enough to keep everyone in this room and a whole lot more people beside very, very, let's call it motivated. Hopefully, and again, I didn't set out here today to answer any questions in the presentation, just again, tell a few stories, give you a little bit of insights to what we're seeing, some of the opportunities in the marketplace, but that is the end of my presentation. Of course.
Just on this last penultimate slide there, you say that
So this one or the one before?
No, on this slide, not the penultimate sentence.
Yeah.
Do you actually see, although I wouldn't disagree with you that it's prevalent, convenient and commercially viable, do you see many large-scale operators actually using alt-net fibre, so to speak? Have you seen it actually start happening yet? Because I do agree with you, it is the most convenient, there's a lot of it out there.
Truthfully, not as much as I would have expected.
Right.
But I suspect that's probably the service providers going, well, it's our asset at the moment, and we're really not quite sure how much of it we're going to want to keep for ourselves. I'm expecting some of them have considered that and have put in enough for themselves and a whole load more besides. It's an interesting, I guess, opportunity for the service providers, but at the same time, I think some of the MNOs are also seeing the value of them perhaps investing in their own physical infrastructure as well.
Which some of them are doing.
Yeah. Exactly.
They're also quite prescriptive as to what they want,
Yeah.
which I guess will also create another challenge.
Exactly, because those involved in that FTTH space are more than aware of the way that those builds have been designed and deployed, and they don't necessarily always dovetail into the requirements of the MNO. Is probably the most politically correct way of suggesting what I am.
Let's keep it at that.
Yeah.
Thank you.
Steve?
We at Gigawatt, we've had approaches to use some of our fibre, and also for us to build central routes from this.
Good, cool. And long may it continue.
Jason, can you use wave division multiplexing in such a way that you can send information on, say, 4 wavelengths, and then use different wavelengths for sensing along the same fibre, or do they have to be on separate fibres?
I'm not an expert about sensing by any stretch of the imagination. My understanding is the magnitude or the requirement for fairly significant amplification associated with sensing technology would most likely be blinded by the magnitude, the amplitude of the ones and zeros from the Ethernet signal, right, that actually the two probably wouldn't coexist well together.
Right. So I'm just thinking about, because you're saying, what's so exciting is the idea of having a single fibre that's going this distance and being able to deliver to 12 properties or whatever. But one of the things we're finding is that you've got fibre that's in the ground that was delivered out for telecommunication, that's not being used, and so suddenly we're finding extra things for it. So it's pros and cons, isn't it? We say, okay, well, let's just roll this out because there's only 2 fibres going through, brilliant. But in 5 years down the line, we might have shot ourselves in the foot.
There are a number of different sensing technologies, and some of them are actually based on a very similar principle to wavelength division multiplexing, using a particular grating pattern that, if that grating changes in length through stresses, for example, imagine it's stuck to the side of a bridge or a skyscraper and the wind's blowing, then you would definitely see different behaviours and characteristics, but you're almost treating it a bit like an OTDR, and so the magnitude of the signals is fairly high. There are other sensing technologies for acoustic sensing, and again, I think there was a presentation last year that talked about those sorts of things. I've got a visual of a fibre existing around a military base, and you couldn't get within 100 metres of it before you got caught, basically. But you can imagine the amplitude of those vibrations are very small, and therefore the amplification needed for that type of sensing technology possibly couldn't exist. Maybe is my bridge going to fall down, fibre grating type setting. Maybe that could, but yeah, I'm afraid I can't answer. I know we've already spent 5 minutes talking about it. I can't answer your question any more coherently than that, I'm afraid.
That's great.
Okay. Excellent.
Okay.
Thanks very much, everybody.